And then to discover that if you try to get answers, that they're related to each other. That the things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. What we're looking for is how everything works, and how everything is, what makes everything work. And what happens first in the history is we discover the things that are on the face of it obvious. And then gradually we ask more questions, and then we dig in a little deeper to things that we can just make. We need to do a little more complicated experiment to find out about it. But it's curiosity as to where we are, what we are. It's very much more exciting to discover we're on a ball, half of it sticking upside down. It's spinning around in space. It's a mysterious force which holds us on. It's going around a great big glob of gas that's burning fueled by a fire that's completely different than the fire, any fire we can make. Well, now we can make that fire, nuclear fire. But that's a much more exciting story to many people than the tales which other people used to make up who worried about the universe, that we were living on the back of a turtle or something like that. They were wonderful stories, but the truth is so much more remarkable. And so what's the pleasure in physics is that, to me, is that as it's revealed, the truth is so remarkable, so amazing. And I have this disease, and many other people who have studied far enough to begin to understand a little of how things work are fascinated by it. And this fascination drives them on to such an extent that they've been able to convince governments and so on to keep supporting them in this investigation that the race is making into its own environment.
As a theoretical physicist, Feynman doesn't have a laboratory, and he finds family relaxation helps him to concentrate. In recent years, he's been concerned with the long-asked, almost childlike question, what are things really made of? What makes up the world we see around us? Have we at last come to the foundation stone from which we can make anything? A tree, a human being? Or must we go on looking at smaller and smaller pieces and going deeper and deeper into a bottomless pit? Feynman is trying to knit together our scattered knowledge of the smallest pieces of matter to see whether they fit a pattern. The problem, although fundamentally important to all branches of science, seems far removed from everyday reality.
The world is strange. The whole universe is very strange. But see, when you look at the details and you find out that the rules are very simple of the game, the mechanical rules by which you can figure out exactly what's going to happen when the situation is simple. It's again this chess game business. If you were in just a corner where only a few pieces are involved, you can work out exactly what should happen. And you can always do that when there's only a few pieces. And so you know you understand it. And yet, in the real game, it's so many pieces you can't figure out what's going to happen. So there was a kind of hierarchy of different complexities. It's hard to believe. It's incredible. In fact, most people don't believe that the behavior of, say, me, one yak, and you nodding and all this stuff is the result of lots and lots of atoms all obeying these very simple rules come out that it evolves into such a creature that the billion years of life with its experiences has produced a thing with prongs that stick out like this and so on. There's such a lot in the world, there's so much distance between the fundamental rules and the final phenomena that it's almost unbelievable that the final variety of phenomena can come from such a steady operation of such simple rules.
But you've had to build the most complex scaffolding to find out the simple rules.
But it is not complicated. It's just a lot of it. And if you'd start at the beginning, which nobody wants to do, I mean, you come in to me now in an interview and you're asking me about the latest discoveries that have been made. Nobody ever asks about a simple, ordinary phenomenon in the street. Oh, like, what about those colors? Or something like that. We have a nice interview and explain all about the colors, butterfly wings, whole big deal. You don't care about that. You want the big final result. So then it's going to be complicated because I am at the end of 400 years, a very effective method of finding things out about the world.
In the search for the ground rules of the physical world, John Dalton worked out a comprehensive explanation over 150 years ago. He assumed that everything we see is made out of tiny atoms, that they're immutable and indestructible, and that atoms of different chemical elements like lead or copper have different weights. Too small to be observed, the atoms combine with each other to form complicated molecules, and vast collections of these molecules are recognizable to us as tables, trees or whatever. But in the final analysis, atoms were to be the smallest constituents of matter, ultimate and unchangeable. At the turn of the century, we evolved our present picture of the atom, light electrons surrounding a heavy central core or nucleus. Once the atom was shown to be destructible, attention turned to the nucleus, and during the 30s it was found that bombarding one nucleus with another led to a release of energy and the breaking up of the nuclei. This process, which takes place in nuclear accelerators, is photographed in a liquid bubble chamber.
You take a liquid hydrogen or some other liquid, and expand it so that it's ready to boil. Low temperature, and you decrease the pressure, it's ready to boil, and it has to form bubbles somewhere. And any little piece of dirt or any little disturbance, it'll form a bubble. In that condition, if a particle comes flying through from some machine, it leaves a track. It tears up the atoms along where electrons are knocked off the atoms along its track. And we can't see that. But when the gas tries to expand, when the liquid tries to boil, the bubbles form around these charged particles which are left. So it leaves a string of bubbles are then formed. Then you can take a picture of the bubbles. So simplest picture would be if you had a machine that made fast particles. Particle would go through, and you see a string of bubbles. But if the particle on the way through hit the nucleus of another atom, then you see a string of bubbles and a kind of a Y if it made its recoil plus some other thing. And instead of a Y, you may see more complicated tracks, 3 or 4 coming out, and then one of them going along and going into 2. Then you know that some particle went along and disintegrated. Now these things are going nearly at the speed of light. And so if you can see a short distance, a few centimeters, that corresponds to 1/10 of a billionth of a second. That is, if a track comes out, it goes along here and then bifurcates into 2. You know you made a particle which integrated into 2 in less than a 10 billionth of a second. So you see, it's not very difficult to find out about these things with clever techniques.
Since the war, with evidence from bubble chamber photographs like this, physicists have explored the nucleus of the atom. The results have been spectacular and confusing. The harder the nuclei were bombarded against each other, the more they disintegrated into even tinier particles until literally hundreds were known. In the last 10 years, some order has been made out of seeming chaos by arranging the particles into patterns. Each pattern has 8 or 10 members, related by nuclear properties like spin and mass. To the physicist, patterns like this imply the possibility of even smaller particles, not yet identified but already named. The key to the question of what makes up the physical world, then, lies in the understanding of the nature of these nuclear patterns.
We're getting close because we have a number of little theories by which we can understand these patterns. One picture which describes what particles you're going to find rather well is that all these particles are made out of something else which we happen to call quarks. And our quark is an object which comes in 3 varieties. It's either an A-type, B-type, or C-type quark, okay? And that the particles that we find are 2 big classes. And one class we can understand as being made out of 3 quarks. And depending on the different proportions, how many A's, B's, and C's, and how they're moving around each other, if we count how many states we would get from putting 3 objects together, it could be made in so many ways, 27 different ways, each one being 3. We find groups of particles in groups of 27 analogously, and so on. A little more complicated, but it's more subtle, but it's like that. And then when we allow for their motion around each other, we find the higher energy states analogous to the way that we ought to get. And even semi-quantitatively, there seems to be a relation